All right, I want you to forget everything you think you know about how the universe works. Today we're diving headfirst into quantum mechanics, the theory that shows us reality isn't some perfect clockwork machine, but actually more like a cosmic casino. We're going to see how science went from thinking everything was certain to realizing it's all built on pure chance.
Okay, so let's break this down. On one side, you've got the classical world, the world we see. You throw a baseball, you know exactly where it's going, right? Its position, its momentum, it's all predictable. But on the other side, that's the quantum reality. Down there, a particle isn't a solid little point. It's what's called a wave function, basically a fuzzy cloud of possibilities.
And this, right here, is the heart of the whole thing. For something tiny, like an electron, the idea of knowing its exact position and its exact momentum at the same time is just impossible. The more you try to pin down one, the fuzzier the other one gets. So our everyday intuition, it just completely falls apart down here. So what do you do then? I mean, if you can't describe something by where it is and where it's going, what's left? Well, the answer physicists came up with is both incredibly elegant and deeply weird.
The answer is the wave function. Think of it like a weather map, but instead of showing chances of rain, it shows the chances of finding a particle. It doesn't point to one spot and say it's right here. Instead, it paints a picture of where it's most likely to be if you go looking for it.
So how do you get from this weird mathematical function to a real-world probability, like a 50-50 shot? It's actually pretty simple. You take the wave function and you square its magnitude. The number that pops out, that's the actual probability of finding the particle at that specific spot. So where that probability cloud looks the thickest, that's your best bet.
And okay, if you thought that was weird, hold on. This is where reality really starts to bend. It's a principle called superposition, and it says the particle isn't just in one of its possible spots, it's kind of in all of them at the exact same time. It's only when you make a measurement, when you look, that this whole cloud of possibilities suddenly collapses into a single, definite reality.
But that brings up a huge question, right? If the quantum world is just this fuzzy, uncertain smear of probabilities, why is it that when we do an experiment, we always get one single concrete answer? How does the maybe of the wave function become the definite yes of our measurement?
The answer is a really cool mathematical tool called an operator. The best way to think about it is like asking the wave function a direct question. There's a specific operator for position, another for momentum, another for energy. When you apply an operator to the wave function, you are literally performing the act of measurement in math.
So the whole process is really this powerful three-step dance. First, you start with the wave function that describes your system. Second, you apply the specific operator for the thing you want to know, say its energy. And the moment you do that, third, the wave function collapses and boom, out pops one single definite number. That's your measurement.
And here's the thing. Every single property we can measure has its own unique operator. What was just a simple position in the classical world becomes a specific position operator in the quantum world. Momentum becomes the momentum operator. And total energy, which gets the fancy name the Hamiltonian, becomes the incredibly important Hamiltonian operator.
Okay, so now we have the building blocks, right? We have the quantum states, the wave functions, and we have the actions, the operators that measure them. But that's just a snapshot in time. How do these probability clouds actually change and move? Well, for that, we need to talk about the master rulebook that runs the entire quantum show.
You know, just like Isaac Newton gave us F equals ma to describe how a cannonball flies through the air, the quantum world needed its own fundamental law of motion. But this one had to describe how these wave functions, these clouds of probability, evolve over time.
And here it is, the time-dependent Schrödinger equation. I know, it looks a little intimidating, but it's one of the most powerful equations in all of physics. Basically, the left side describes how the wave function is changing with time, and the right side shows how the system's total energy, that Hamiltonian operator again, is acting on the wave function. This thing is the engine of quantum evolution. So here's the key takeaway. The Schrödinger equation is the master recipe for the quantum world. If you know the state of a system right now, this equation lets you predict its entire cloud of probabilities for any moment in the future. What's wild is that it's perfectly predictable for the wave, but totally probabilistic for the final measurement. Now, as you can imagine, writing out these super complex wave functions and operators all day can get really messy. So to make life easier and to actually get deeper insights, physicists developed some incredibly clever and elegant mathematical shorthands. This complexity led to a huge breakthrough. Instead of writing out the whole messy wave function, a physicist named Paul Dirac
came up with a brilliant shorthand. Now you can represent an entire quantum state with just a single clean symbol called a ket. It's all the same information, just packaged way more neatly.
The absolute genius of this is that it lets physicists treat these quantum states like they're just little arrows, or vectors, in some abstract space. And when you do that, it transforms a ton of complicated calculus problems into something much more intuitive, simple algebra and geometry.
And this new algebraic approach doesn't just work for the states. Those operators we talked about, like the Hamiltonian for energy, they can be translated into this new language too. They become simple grids of numbers, which you probably know as matrices.
And this is a total game changer. It means we can take a ridiculously complex quantum problem, translate it into the language of matrices and vectors, and then solve it using the powerful tools of linear algebra. And you know what's really, really good at linear algebra? Computers. This blew the doors open for solving all kinds of problems.
So let's just recap this incredible journey. We started in the classical world, where a state is just a definite position and momentum. In the quantum world, it's a wave function of probabilities. Classical measurement is just looking, quantum measurement needs an operator. Classical evolution follows Newton's laws, quantum evolution is guided by the Schrödinger equation. The bottom line is, we've moved from a reality that was supposed to be deterministic and predictable to one that's fundamentally based on chance.
And that leaves us with one final profound question to think about. If the very fabric of reality, at its deepest level, is just this shimmering cloud of possibilities, why does our world feel so solid, so predictable? That gap between the quantum fuzziness and our everyday certainty, well, that's one of the deepest mysteries in all of science, and it forces us to ask what reality even is.